Okay, welcome everybody to lesson 2.3 about polynomials. And in this one, we're going to talk about the rational root theorem. So this one's a bit of a doozy. Got lots of proofs that we're going to look at today and cap it off with an example at the end. So buckle your seatbelts because it's going to be a little bumpy ride. Okay. So last lesson, at the end, I made this grand statement that, like, if you've got a polynomial with integer coefficients, whole numbers, positive or negative whole numbers, then any zero that's in a whole number or an integer is going to divide the constant term. So why is that true? Why is it true that all the integer zeros are going to divide a zero constant term? And we're going to look at proof of this today. So this is not the rational root theorem. The rational root theorem kind of is an extension of this. So we'll start off with some things we know about, and we're going to start off with some simple cases like a linear function. So I wrote the linear function as a polynomial. A1 is our first coefficient. That's the slope. So don't be scared by this notation. A1 is just a coefficient for the x to the 1 power. So in traditional linear fashion, this would be m, and A0 would be b. But I'm just going to give them those subscripts. They don't mean to do anything mathematically. They don't mean multiply by 1 or raise it to the 1 power or anything like that. They're just saying this a is different from that a. We're both going to use a for our coefficients, but I'm going to say a1 is the coefficient for x to the 1, and a0 is the coefficient for x to the 0, but that's our constant term. So that's our setup. We've got a polynomial that's linear, a1x plus a0. So then suppose we've got an integer root. So r is an integer root. What does that mean? Then that means that when you plug in r, you get 0 as an answer. So we plug p of r in, and that gives us a1 times r plus a0. So we're just plugging the integer root in. Okay, so let's we need to say that r divides a0. It's not obvious that it divides a0, but let's figure out what we can do. Well, we're going to subtract a0 from both sides. So when we subtract a0 from both sides, we're going to get this equation now. So a1r equals negative a0. Okay? And the next step we're going to do is we're going to divide both sides by r. Okay? So dividing both sides by r gives us this statement, that a1 equals negative a0 divided by r. Now this over here, this looks like a fraction. This looks like a rational number. But it can't be. And that's because it is in fact, well, it's not a fraction, it's a whole number, it's an integer. And that's because a1 is an integer. And so we have an integer on the left, and it equals an integer on the right. It must equal an integer on the right because they're equal to each other. And so a1 is an integer, so that means that negative a0 must be an integer. And a0 over r being an integer means that a0 is divisible by r. It means that r is a factor of a0. For example, if a0 was 8, then the only things r could be are 1, 2, 4, or 8. Because we need the result after you divide this to be a whole number. We need that to actually be a whole number because it equals a1, which is a whole number, which is an integer. Okay? And so this is exactly gives us our list of integer zeros for the linear case. Now let's look at the quadratic case. Okay, so now suppose we've got a quadratic. a2 x squared plus a1 x plus a0. Remember A0 through A1 or A2, so each of these guys are integers. So these are ints, which means, again, positive or negative whole numbers, right? 5 or negative 2. They're not fractions. Okay, then we plug in r. We're assuming that r is an integer 0 of p. So we plug r in, we must get 0 out. So now those powers are doing math. So a2 is not a power, but that's the first constant, first coefficient. R squared plus a1 r plus a0 equals 0. So that's what it means for r to be an integer, to be a 0 of p. We're going to do the same thing we did the last time. Subtract a0 from both sides. So now we have a2r squared plus a1r equals negative a0. Now we're going to divide both sides by r again. And what does that get us? Well, when we divide everything over here by r, so we divide over here by r, and we divide over here by r. Well, that's going to cancel each of our powers by 1. So it diminishes the power of r on each term by 1. So we have r squared over r gets r, and r over r gets 1. And so the a2r squared becomes a2r, and the a1r becomes a1. Okay, so what does that tell us? Well, it tells us that we have an integer here on the left. This is an integer. Why is a2r plus a1 an integer? Well, an int times an int is another integer, right? Any whole number times another whole number gets you a whole number. 2 times negative 3, that's going to get you another integer, negative 6. And then if you add an int plus int, you get an integer, right? Anytime you add integers, you get another one. And so over here, we have an int. And so we have an integer equals a0 over r. And so again, by the same reasoning, a0 divided by r must be an integer. So r has to be a factor. Let's get our ink back on there. So that means that this thing over here is an integer because we have an int on the left, and so and it equals the thing on the right. And so we have to have r being a factor. Okay, so we just did it for the linear case, we did it for the quadratic case. Now, this works for any polynomial. So here's our general case. So now I've got to list the polynomial in its general form, which is some coefficient times some power of x, some positive power of x, plus another coefficient times the power of x that's 1 less, plus another coefficient, and so forth. So our powers kind of decrease as we go to the right, all the way till we get x to the 1, and then our constant term at the end. Okay? And then each of these a n minus 1, those are just coefficients for those powers of x. Okay, now let's suppose r is an integer 0 of p. That means we plug it in, we get 0 as an answer. Okay, similar, exact same 2 steps we did the last time. We subtract a0 from both sides. So we subtract a0, and that's going to give us an, r to the n, plus an minus 1, r to the n minus 1, plus so forth, until we get a1r equals negative a0. Okay? So now we're going to do the same thing we did last time. We're going to divide both sides by r. So everything over here is divided by r. Everything over here is divided by r. So what's that going to do to the right-hand side is obvious. That's negative a0r, so that's easy to see. The left-hand side, what does that do? Well, each term is being divided by r. And when we divide the first one by r, that just subtracts 1 power away. So now we have an r to the n minus 1. For example, if it was an, well, let's actually put numbers in here. Suppose it was, 3 r to the 5th, if I divide this by r, then I have 5 r's on top and I have 1 r on bottom, and so that's going to turn this into r to the 4th, 3r to the 4th. So it takes away 1 from the power. So the first one goes down in power. The next one goes down in power. So n minus 1 is n minus 2. Then so forth. Each one of those has a power of r. They're getting smaller and smaller until we get to the last one, in which case r divided by r is 1. So the last one just becomes a1 times 1. So we have on the left this really big, long expression, but the important thing to realize is that we have an integer here because an is an integer, and r to the n minus 1 is an integer, because any multiple of an integer is an integer. So we have an int, and then we have another int. These are all integers. We're adding together a whole bunch of integers. And so the left-hand side, all of this whole thing over here, this sum is one big, right? And on the right-hand side, that means we have to have an integer. So then we have to have a0 over r as an integer. And so that means that, again, r is a factor of a0. And that works no matter what our polynomial's power is. What kind of polynomial it is, as long as everything is an integer coefficient, then all integer zeros will divide the constant term. Okay, so that's the feel for this. We've got to get integer equals something. That's how we show that that's divisible. Let's look at the rational root theorem next, which we'll prove again. We'll prove the rational root theorem. It's a similar proof. So rational roots, as opposed to integer roots, rational roots, I don't know, I guess people could say rational zero theorem, but I think rational root sounds better. Suppose we want to find all the rational roots of a polynomial. So we're looking for roots that look like a over b. So some constant, some integer over another integer. The rational root theorem tells us how to find all of these. So here's the rational root theorem. Suppose we've got a polynomial with integer coefficients, and the leading coefficient we'll call an, and the constant term we'll call a0. So this is just a general setup, okay? So this is just your typical polynomial. Typical, and I've labeled the constant term and the leading coefficient. An is the leading coefficient, a0 is the constant term. Then, if a over b is a rational root, that means that a and b are integers. If it's a rational root, then a is a factor of a0, and b is a factor of an. So this means that a divides the constant, and b divides the leading coefficient. Okay? So all the factors, all the possible rational roots will be factors of the constant term divided by factors of the leading coefficient. So we'll enumerate those in the example at the end. Okay? So this is the rational root theorem. It gives us a list of all the rational roots that a polynomial with integer coefficients can have. Okay? All right. So why? Let's dive in. Okay. This proof is a little bit long, but hopefully you get the gist of it. It's very similar to the integer zeros that we just looked at. So here's our setup. We've got our polynomial, our general polynomial over here, an x to the n plus an minus 1, x to the n minus 1, plus so forth, all the way down until we get to our constant term, a0. And we're supposing a over b is a 0. And let's go ahead and make sure that our rational number, a over b, has been reduced, which means that there's no common factors between a and b. You can always reduce a fraction, right, down to lowest terms. So we'll just go ahead and assume that a over b has been reduced down. And that's what this means. No common factors means a over b reduced fraction. You know, like not 2 over 4, 1/2 is the reduced fraction of 2 over 4. Okay, so we want to show that a, capital A, is a factor of a0, and b, capital B, the denominator, is a factor of an, the leading coefficient. Okay, so let's go ahead and do each part. We'll do the first part, show that a is a factor of the constant, and then we'll do the second part, b is a factor of the leading coefficient next. Okay, so first let's show that a is a factor of a0. So what do we know? Well, we know that if you plug a over b out, so let's do that. So we plug a over b in, and so everywhere there's x gets replaced with a over b. So we have an, a over b to the n power, plus an minus 1 times a over b to the n minus 1, and so forth, all the way down to the constant term, a0, which has no a over b multiplying it because, you know, it's not being multiplied by x. Now we subtract a0 from both sides. Oh, this should feel kind of familiar to the first one, where we're getting a0 by itself, and I need to get the left-hand side to be an integer so that we find that that a0 is divisible by a, that big A divides a0. All right, so what will we do next? Now for a little bit of a trick. We've got all of these numbers are rational numbers, so we've got a bunch of rationals. I want to make them into an integer. And to do that, we have to get rid of our denominators. So how are we going to do that? Well, we're going to multiply it by the highest power of b. So we're going to multiply this by b to the n. And so I'll just show you how it works for the first one. So we have a to the n over b to the n times b to the n. And so we have nb's on top now, nb's on bottom, and so those cancel. And that gets me a to the n. Oh, that sounds weird. A sub n, little a, times big A to the n power. Okay? And you'll see each time we multiply by b to the n, we're going to go to the right, increasing powers of b. And the last one we've got, I'll just show the last one, a1, a over b. This is our first degree term, multiplied by b to the n. Well, there's one b on bottom, and nb is on top. So that's going to turn this n into n minus 1. So that's what's going on right here. So a1, a. Now, the details of these numbers aren't that important. What is important, though, is that now we've got an integer on the left. Well, we're not quite done. We're not quite done because we haven't said that a divides. So the next step is to divide both sides by 1 power of a, by a itself. What does that give us? Well, if you look over here on the left, you can see everything has big A, right? There's an a here. Each of these middle terms are going to have higher powers of a. We have a to the n minus 1, and the last one, the biggest one, is a to the n. So if we divide everything by a, that just decreases each power of a by 1, all the way down until this guy, in which case we divide that one by a, and it cancels with the a that's... And so we still have an integer over here. This is an integer. Because an is an integer, an minus 1, each coefficient is an integer. Big A is a whole number, big A is an integer, and big B is an integer. And we're just multiplying out and adding lots and lots of integers together on the left. And so that tells us that over here must be an integer as well. So that's an integer. And now we see the fact that B and A have no common factors, and yet that's an integer. So the only way for this thing to be an integer over here, because B and A have no common factors, so because of this, that means that A0 over A. And so that says that A is a factor of A0. It comes down to the fact that over here on the left we have an integer, and on the right we have an integer, and so the only way for that to be true is if that fraction A0 over A was actually a whole number. And so big A has to divide A0. Because it's not dividing b to the n because they don't have common factors. Okay, so that's showing a is a factor of A0. Well, that's kind of just a general, it's a generalization of the one that we did earlier. We already know that if it's an integer 0, then it divides A0. Let's look at b being a factor of an. Okay, same starting place. We know a over b. If we plug that in, we get 0 as our answer. So you plug a over b in, and that yields 0. But now we're going to get the an by itself. We're trying to get an isolated. We're going to subtract an, a over b to the n, this whole thing. That's the leading term. We're going to subtract that from both sides. And that's what we get now. Right? So now our leading term on the left is this guy. Then we have all the stuff in the middle. And then we have a1, a to the a over b, and then we have a0. The next step is to multiply both sides by b to the n minus 1. So what does that do? So we multiply everything by b to the n minus 1, which is the highest power of b on the left, both sides. So when we look at the first term, we have b to the n minus 1 on the bottom times b to the n minus 1, and so that cancels. So a n minus 1, a to the, let's erase more time, n minus 1, a to the n minus 1 over b to the n minus 1 times b to the n minus 1. These b to the n minus 1s cancel, so you're left with a n minus 1 times a to the n minus 1, big A to the n minus 1. And each of these other terms of b are going to cancel and get bigger and bigger and bigger until we get to the first degree term, so a1, a over b, multiplied by b to the n minus 1. Oops, this should be b to the n minus 2. Because we have one b on the bottom, so you have b to the n minus 1 over b. You cancel 1, and you take away 1 from the power. So this is b to the n minus 2. Again, suppose I have, for example, if I've got b to the 5th over b, you know exactly that this is b to the 5 minus 1. Right, which is equal to b to the 4. So we take away 1 from this guy's power up. Okay, and so each of these powers of b gets bigger as we go to the right. But that's not really the important thing. The important thing to realize is that this whole statement over here, this entire expression on the left, this being n minus 2, is an integer. And so we have an integer, this must equal an integer. And since we have an integer that says that an over b times a to the n is an integer, that this whole thing is an integer. And we already know that a does not divide b, big A and big B have no common factors, so that says that an over b is our integer, okay? Because big A to the n doesn't divide b doesn't divide big A to the n. They have no common factors. And so big B must divide a sub n. So big B is a factor of a sub n. Alright, that's the rational root theorem in all its glory. It's quite a lot, but it's all algebra. It's all just algebra. Understanding what does it mean for two numbers, for a number to be an integer, and understanding basically how integers behave when you multiply and add them together, and what does it mean for something to be a root. So that's fundamentally what it comes down to, is how do you get integers, and how do you know when something divides something else? Is that the result is an integer when you... Okay, so that's the rational root theorem. And let's go ahead and use it in an example. We're going to list all the rational roots of this polynomial. We're going to guess and check the roots and then factor it completely. Okay, so the list of rational roots, they've got to be in this form. They have to be some factor of the constant term. So I'll highlight the constant terms. So our constant term is -6, and our leading coefficient is 2. So all the rational roots, that means any root that is a rational number, any 0 that's a rational number, of this polynomial is the numerator must divide 6, and the denominator must divide 2. So all of our factors of 6 I've listed up here, 1, 2, 3, and 6. And all our factors of the leading coefficient are 1 and 2. I've listed those down there. So that's going to give us 12 possible rational roots that we can check, that we can throw into the calculator and see if they are actually zeros or not. Okay, what are those 12 numbers? Well, you have 1. So we have 1, 2, 3, and 6. And that's all from dividing by 1. So we have 1 over 1, 2 over 1, 3 over 1, 6 over 1. So those are the possible integer zeros, right, from the integer zeros theorem that we looked at earlier. And then we have the rational ones, which are 1 over 2, 1/2. Now 2 over 2, we actually already listed that. 2 over 2 is 1. So we've already listed that. We have 1, 2, 3, and 6. Also plus or minus, don't forget, plus or minus 1/2. We already listed 2 over 2. We have 3 over 2. We haven't listed that one yet. And then 6 over 2 is, in fact, already been listed. That's 3. So we've already listed out 6 over 2. That's equal to 3. So we have 12 possible things here. 1, 2, 3, 4, 5, 6. And then the positives and negatives. So that's okay. And so I did some guessing and checking on this problem. You can plug them into a calculator and figure this out. But I found -2 was a root, and we can just go ahead and evaluate it to check. So if we plug 2 in, we get p of -2. We get 2 times -2 to the third minus -2 squared minus 13 times -2 minus 6. And I say that this is in fact a 0. So the first one's -8, so this is -16. And then we have -4, because that's -2 squared is 4, so -4. And then we have plus, this is 26. And then we have -6. And let's just see that that is in fact equal to 0. -20 plus 26 minus 6, yeah, that's equal to 0. Okay. So that says that x plus 2 is a factor. So we found 1, so we're going to go ahead and make the problem simpler by using polynomial division. So let's go ahead and do our polynomial division on this and see that it gets to be a simpler polynomial. So we'll have 2x cubed plus 4x squared, subtract that, and then we get -5x squared, so now it's minus 5x, and bring the -13 down, -13x, -5x squared minus 10x, take that away, -13 plus 10 is -3x, bring the -6 down, minus 3, and then that's going to give us -3x minus 6. Take that away, and we get 0 remainder. So that says then that this equals x plus 2 times 2x squared minus 5x minus 3. And this quadratic we can factor using our quadratic factoring techniques, namely the guess and check method. 2x and x need to be the first two terms, and then I need numbers that are going to multiply to get -3, and I can see right away that this is -3 and this is +1, because 2x times -3 is -6x, and 1 times x is 1x, and -6 plus 1 is -5, the middle term. And so we've factored the polynomial out, and so we're done. The polynomial is 2x plus 1, and then x minus 3, and then x plus 2. Okay, and the order doesn't matter, you write these things in. So we would have 3 zeros from this. We could write the zeros, we'd have -2 as from this one, we'd have -1/2 from this one, and then we'd have +3 from this one. We'd have 3 zeros for our polynomial. Okay, so rational root theorem gives us a list of things to check. It allows us to enumerate all the possible rational roots. We can start plugging them in and seeing which ones work, and then when we find one, we can long divide it out, make the polynomial simpler and easier to solve. And you should note that all of our rational roots, -2, -1/2, and 3, those are in fact represented back here, right? You can see -2, -2 is this guy, -1/2 is this guy, and +3 is this guy. So there's no rational roots that aren't in this list. Okay, that's it. That's the rational root theorem. We're probably not going to do too much more proofing stuff in this unit, but I figured it's good to give you kind of a reasoning why the rational root theorem works, why it is the way it is, and the integer zeros, rather than just waving hands and saying, hey, you know, it's magic, just trust me, rational roots, you know, they're factors of the constant over factors of the leading term. So, yeah, so there's actually math backing it up. Okie dokie, I'll see you guys tomorrow.